So this is called the ideal gas law. If you notice, it has pressure, volume, temperature, and moles. We have done calculations with all of these. We've done calculations with pressure and volume. So if we have pressure and volume, what is that law? Where we say P times V equals P times V. You remember, we have four choices. Charles, Gay-Lussac's, Boyle's, and Avogadro's. Boyle's. So P times V equals P times V, just like you did on your board. That's Boyle's law. Okay? We also have I'll review these at times for you because on the test on Thursday, you'll need to be able to differentiate between the different laws and who did what. Okay? So that's Boyle's. If we take V over T and solve for that, that's which law? So we can eliminate Boyle's, so we've got Gay-Lussac's, Charles, and Avogadro's. Charles, very good. Okay, then the next one we have is V over N. What law would that be? Avogadro's is right. You don't have to write this down because you already have these laws written out. Of course, the last one is pressure over temperature, and some of you guys did that relationship on your board, and that would be Gay-Lussac's. Okay? So if you combine all those and look at the relationship, it would look like this over here. Now the only thing is, what I throw in there is this R value. So you're like, where did that come from, that R value? Well, we're not going to do a beginning and ending when we use this law. It's going to be like instantaneous. It's kind of like when you're on the road and you go, well, what did I start out with speed? Well, I started out with 0. I was in park. And then I sped up, and so you can look at before and afters and something like that, but sometimes the instantaneous is when you see the cop alongside the road and you go, oh, where's your eyes usually go? To the speed, right? Or your foot goes to your brake, right? To slow down. None of you are like that. You just go along the same speed because, hey, I'm obeying the law. I'm not going to get pulled over or anything, right? This allows you to find pressure, volume, and temperature moles at any time. It's called an instantaneous look. You go, hey, I've got this gas and I've got it at these conditions. How many moles do I have? Or what's the temperature that I have? So it's not a beginning and ending. It's not like, here we are at the start, here we're at the end, and what's the beginning and ending? It's not like that. It's like at any set time, you can look at a gas and get its volume, and get its temperature and pressure. And you can get all that stuff all at once. So it's really, really handy because it allows us to... We could do a beginning and ending with that, but if we do that, we've got the other laws to work with to do that. So we don't need it. So we got this R value. I'm going to show you guys how you calculate it, but you won't have to calculate it past what we're going to do right now. Okay? So let's set this up. This PV equals nRT. Set it up on your paper to solve for R. Let's just go ahead and isolate capital R. I want you to isolate it. So just do that on your paper real quick and switch the symbols around to solve for R. And then we'll see if you've switched them around correctly. So go ahead and do that real quick. Okay, so you went ahead and said R is equal to PV over NT. Is that correct? Okay. All right. So keep that in the back of your mind. We're just going to look at that. I need to talk to you a little bit about this thing called molar volume. Okay. In fact, on Thursday you're going to do a lab and you're going to try to come up with this number. So this is a number you guys will need to come up with or try to come up with as for comparison. It's 22.4 liters. That's what you're going to try to solve for. Okay? But you're not going to create a volume of gas this size. So this size is a volume, and it represents 22.4 liters. It's about 5 gallons. So this represents 5 gallons, or a little over 5 gallons of air. Okay? So that, we want to use liters, though, to do it. And so we got this thing that's called 22.4 liters that I'm going to go ahead and share with you. And it's at STP. So basically, this represents 1 mole of particles. All right, so this box is measured 28.2 by 28.2 by 28.2. And if we multiply that, we get centimeters cubed. And we would get a number that would be 22,414 centimeters cubed, which translates to 22.4 liters. Okay, so we don't have to use thousands. And so that's what the volume is taken up. So if I open this up and look inside, I see 6.02 times 10 to the 23rd molecules. That's how many's in there. Okay? I can't see it. But I know, and through experimentation, if this, but it has to be in certain conditions. Okay? So the conditions are right here. So you guys see what conditions that gas needs to be under to have that volume? What's the conditions that gas has to be? What's the standard? This is called molar volume at STP. So STP stands for standard pressure and standard temperature. Did that out of order. So what's the standard temperature on that box? It is, what is it? 0 degrees Celsius. So it's 0 degrees Celsius or 273 Kelvin. Okay, what's the standard pressure? 1 atm. Now it could be 1 atm, but what else could it be? Does anybody want to say, what's another way to measure standard pressure? We got 1 atm, what's another way to measure pressure? So we got atm, we got, what's a barometer measure? It measures a height, so what's the height? You guys have, it's in your notes, but millimeters of what? Mercury. Okay? So 760 millimeters of mercury. What's the last thing it could be? If I didn't have either one of these two, and you had a third one, what's the third one that I gave you in your notes? KPA. I kind of feel like that guy today on Ferris Bueller. You guys ever watch Ferris Bueller? Yeah. Anyone? Anyone? It was did world history, and nobody was responding. They were all kind of drooling. So I hope you guys. I guess the 5 days away has been kind of rough on you. Okay. Hopefully you'll get more engaged here. Okay. So here's the deal. This is 22.4 liters of gas. What conditions does it have to be under? What's the conditions? Standard temperature and pressure, STP. What's the standard temperature? 0 degrees Celsius. And what's the standard pressure? 1 atm or any of those. Okay? So this is called like a standard volume. And that's 1 mole. It's kind of like having a meter stick and saying, hey, this is exactly 1 meter. Everything's referenced against that. Okay, so if I cut this in half, I go, boom, cut it in half. How many moles do I have? Half a mole. Okay, what if I double it? Hey, I'm doubling this. How many moles do I have? 2 moles. Okay, what's the volume of 2 moles? 2 times 22.4, 44.8. Okay, what if I had 1/10 of this? What if I had 1/10 of this? What's the volume? 2.24, right? So it's just a ratio. That's all it is. And if one changes, then the other one changes to that. And we'll do a couple problems with that, and they're really easy. Okay? So this is, we're going to get you active, get you doing something. Remember this equation. It says R. What we're going to have you do is plug in these numbers on this box and find R for the 3 different pressures. So, first 2 rows. Okay? What do you need to solve for R? First 2 rows. Look at your equation. To solve for R, what do you need? Pressure, volume, temperature, moles. Do you have temperature on there? Yeah. Do you have pressure on there? Okay. Do you have volume? Okay. Do you have moles? Okay. Plug it in. Got it? Okay. The only thing different, middle 2 rows, you don't have atmospheres. You have to use millimeters of mercury. So everything's the same as that row. You're using, for your pressure, millimeters of mercury. You got it? So you got the volume, temperature, moles, and the pressure. And it's on the board. The pressure was on the board. I can put that down again. Last 2 rows, you guys are using kPa. So you're using the same pressure, or I'm sorry, you're using the same volume, temperature, and moles, but you're using kPa as your standard pressure unit. Okay? So you need to do that, and I'm going to come around and look at your answers so that you're active and not just sitting there. And so first row, 2 rows of atmospheres. Second 2 rows, you're using 760 millimeters of mercury. And last 2 rows, you're using 101.3. You're using R equals PV over NT. You solving for your R value. Okay, go ahead and do that. Give you 1 minute. Because all you're doing is plugging numbers in. So I want to see your answer. Go ahead and do the calculation. Give you a minute. Write the answer down. You do not use PV equals nRT to solve for it. You use one of those 2. Okay? Okay, so you don't plug in pressure and volume. You can do it that way. It's a lot longer process. You could do it that way. But it's a lot longer process, so you don't want to do it that way. You want to go the easy way out. Yep. Gotta have your units. Gotta show them. What'd you get? I don't know. 1.5 moles out in front. And you have to times it by 22.414 liters over 1 mole.
It's got 149. That's what I
Okay. You get it? Get it?
I don't know. There's no way that's.
Get it?
I don't know.
Not yet.
49.4.
Haven't had a lot of success yet, so my 90% is way out of whack. No, You gotta logically look at your answers, guys. So if you come up with a number, it's 149, which I see. Okay? Logically, you look at your answer and go, okay, this is 1 mole, and it's 22.4 liters. Now I have 0.15 moles. And some of you say, well, that's 149 liters. So that would be like this, 7 times this size. You go, wait a second, that cannot be because 0.15 moles is a lot less molecules, so it should be a less volume than 22.4. So if you set it up one way and got like 149, you're like, no, that's not right. Cannot be the case. Alright, so relook at it. You got 149, relook at it. See what you can do to solve for it. You get it?
0.0 liters.
No?
Okay, if you want to round it out.
Nuh-uh.
Is this
Why?
32?
Because you just a guess.
That's not what I got.
Oh.
Well, maybe the next one we'll get 90% agreement. This one we got about 10 agreement. So, here we go. So here we go. 0.15 moles out in front. A lot of you guys do not still, when you got units, you're still like, I'm just gonna guess. I'm just gonna divide it. And so some of you took 22.4 divided by 0.15 moles. There's my moles. Over here goes moles. Over here goes liters. For every 1 liter, how many, or 1 mole, how many liters do I have? 22.414. Moles cancel. End up with liters. My answer is 3.4. Okay? Guys got to use your units. Some of you just like to get this. There's 3 ways you can do the problem. Take 22.4 divided by 0.15. Take 0.15 divided by 22.4. Multiply 0.15 times 22.4. You get a 33% chance of getting it right. Use your units. You'll never get it wrong. Okay? So here I'm looking for 90% on this one. 90% on this one. Now, before I have you guys do this one, I need to tell you that if something's in milliliters, it has to be put in liters. So ideal gasoline needs liters. Be used all the time. So, again, there's 1,000 milliliters in a liter. I can come up with 2 answers. I can multiply that 1,000 times 250. I get 250,000 liters. Or I can divide 250 by 1,000. I come up with 0.250 liters. Which one is more logical? 0.25. Okay, but I guarantee you, I get people that multiply it by 1,000, they come up with 250,000 liters. Okay, for every 250 milliliters. 250 milliliters is just a little bit. So when you do this problem, you're going to have to use 0.25 liters to plug it in. So go ahead and solve for this one, and we'll see how many moles we have. So here is 22.4 liters is equal to 1 mole. Now we have 250 milliliters, which is a beaker, 250 milliliter beaker of air. How many moles of particles does it have? So go ahead and do that problem and write an answer down, and we'll look for 90% on this one. So that would be your answer, 0.011 moles. Make sure everything's in liters. The pressure can be in anything you want it to be, but you got to make sure the R value you're using is correct. Temperature has to be in Kelvin. Of course, moles have to be mole. So I'm going to give you a problem. So it says calculate the pressure. So pressure is unknown. The pressure needs to be in torr, or millimeters of mercury. They mean the same thing. Let's say you have 0.95 moles of a gas. Doesn't matter what gas it is. This one's argon. And you place it in a 4.5 liter container. And the conditions are a little cooler. Might be in a freezer, for example. It's around a minus 7.35 degrees Celsius. So what I've done to help you out, I've got the moles written in. I got to use R that's 62.4. And why? Because it wants to know the pressure and torque. So I go to my R values and realize R constant for pressure and torque is 62.4. So I write that down. Then the temperature, I don't write a minus 7.35. I go ahead and take 273.15 minus 7.35. I get 265.80 Kelvin. Then my volume is 4.5 liters. So go ahead and solve for the new pressure. So go ahead and plug that, switch this equation around, and solve for the correct pressure with that equation. So now you're just isolating your variable, solving for it.
We're gonna hand this in.
Yeah, this will be handing in like the last one. I'll check your work and that. So, again, 3500 torr. Your assignment is a mixture of these two type of problems. And they start out with these type of problems first, where you got to go PV equals nRT. That's the first thing that you have to do. So, your assignment is page 346, 55, 57, 58, 59, 53AB, 54CD. So that would be 8 problems for Thursday. Okay, you have a little time tomorrow to work on them probably. I need to talk to you a little bit about the lab. Need to talk to you a little bit about maybe give your assignment back, but we need to go over one more law before we can do the lab on Thursday.
So hand in the assignment that was due today.
Yeah, that assignment due today, you need to hand in eventually.